Hello everyone, thank you for coming. This is the brave new world of JavaScript engine vulnerabilities. I'm Simon Zuckerbraun. I'm technical lead at the Trend Micro Zero-Day Initiative. First, just a few words about who we are. The Zero-Day Initiative is the world's largest vendor-agnostic bug bounty program. Each year we purchase over 1,000 vulnerabilities from independent researchers worldwide. And these researchers who choose to disclose responsibly are paid for their hard work. Trend Micro Research uses the intelligence that we gain from these zero-day reports to defend our customers. And every vulnerability that we purchase is also reported promptly and free of charge to the vendor of the vulnerable product for resolution. A discussion of JavaScript security must begin with the web browser. From the outset, web browsers have been a major contributor to the attack surface of desktop and mobile devices. If you consider what typically runs on the end user's device, it's plain to see that the browser tends to dominate both in terms of complexity of the application and also in terms of the number of interactions that it has with external entities over the internet. On a typical day, a user will visit dozens of websites which will bring in additional resources from hundreds of secondary internet locations, and each one of those has access to many thousands of APIs and other features that the browser offers every time it processes remote content. Looking specifically at what parts of the browser attack surface have yielded the most vulnerabilities, from our vantage point at the Zero-Day Initiative, we have noticed a major shift take place. Prior to 2016, most vulnerabilities discovered were in the implementation of the various APIs that the browsers offer, and specifically in the DOM APIs. And the DOM APIs are the methods that are implemented by the browser that web pages invoke in order to manipulate displayed HTML in an object-oriented fashion. In fact, when DOM API vulnerabilities were at their peak in 2014, the Zero-Day Initiative was purchasing approximately 40 DOM vulnerabilities in Internet Explorer per month. Since then, DOM API vulnerabilities have been in steep decline, and this is largely due to effective mitigations that have been put in place. So today, in late 2019, it is rare to see an exploitable DOM API bug discovered. From 2016 and on, however, there has been another less happy pattern as vulnerabilities began to emerge in an entirely different area of the code base of major browsers, and that is in the JavaScript engine. To be clear on this point, a JavaScript engine is the code that parses and executes the JavaScript language itself. The engine does not include the implementations of all of their various APIs that can be invoked through JavaScript. In recent years, the JavaScript engines of the major browsers have become a rich source of vulnerabilities. What is worse, vulnerabilities in JavaScript engines tend to be highly critical in impact. Contrast this with the DOM vulnerabilities of years past. A typical DOM vulnerability would give the attacker the ability to perform a very tightly constrained form of memory disclosure or memory corruption. For example, perhaps some DOM API could be tricked into writing a fixed value to a single memory location. To exploit such a bug, an attacker first needs to perform a large number of carefully choreographed operations to arrange allocations in memory in just the right way so that the memory corruption that's triggered by the vulnerability will affect some particular structure that the attacker can use to their advantage. In many cases, it was even necessary to combine two DOM vulnerabilities in a chain, one DOM vulnerability to disclose sensitive information from memory that was necessary for setting up the next stage of the attack, and then a second DOM vulnerability to actually do the memory corruption that results in remote code execution. In contrast, a JavaScript engine vulnerability is always catastrophic to process security. Exploiting a JavaScript vulnerability immediately gives an attacker everything they need to execute arbitrary code within the browser process, although modern process-wide mitigations can still throw a few speed bumps in the way. Now, it may seem somewhat surprising that JavaScript engines harbor large numbers of bugs. After all, JavaScript is only a language. It has a fairly modest library of standard objects. Unlike the DOM API, JavaScript by itself does not offer a sprawling menagerie of objects and methods. So why is it that the JavaScript engine is so hard to secure? Well, the fundamental answer is that JavaScript is a highly dynamic, loosely typed language. Also, for historical reasons, it has a lot of idiosyncrasies. And in the slides to come, I'm going to go into some detail about what that means. But the bottom line is that JavaScript is a language that does not lend itself well to high-performance execution. But as of today, JavaScript has become the language that powers the entire client-side portion of the web, plus a significant chunk of the server-side portion as well, plus many other things such as apps written using the Electron framework. So to meet the demands of all of these applications, high performance is a necessity. This means that the developers of JavaScript engines have had to expend enormous effort on the problem of performance. It's an enormous implementation challenge. I believe that there's a dynamic at work here that's known as a Red Queen's race, which is an interplay between stakeholders that results in a continually shifting goalpost. Originally, JavaScript was envisioned as a scripting language for performing lightweight operations within web pages. For example, the user clicks on a button, and the script displays warning messages for any required fields that haven't been filled in. Simple operations like that did not require any special effort to achieve good performance. Over time, web developers began to push the envelope on what JavaScript could deliver. And since the original JavaScript implementations were naive in regards to performance, that soon resulted in laggy web pages. In an effort to make their browsers highly responsive again, the browser providers started to soup up their JavaScript engines with more sophisticated code in order to help JavaScript run more quickly. But when web developers found that there was significantly improved JavaScript performance at their disposal, then they started to push the envelope even further, necessitating another round of performance improvements on the engine side, and so forth. Also, not surprisingly, we've also seen a lively rivalry between the major players as they compete to offer the most responsive browser experience. So now let's start to drill down a bit into what makes it challenging to execute JavaScript with decent performance. Here's a little example. Let's say the browser is executing some JavaScript code on a web page, and the JavaScript code creates some objects that have width and height properties. And within the JavaScript code, there's a function written just like this one here, total width, that's just supposed to calculate the total width when it's given two objects. Now, when the engine goes to execute this function, it's clear what it's supposed to do, right? It should retrieve the width property from the object specified in parameter A, and then it should retrieve the width property of the object specified by parameter B, and add the two numbers together and return the result. It's pretty easy. And it's clear that if we hope to get any kind of decent performance out of our JavaScript execution, the engine had better be able to execute this simple function very quickly and efficiently. Shown here is what we'd like to achieve in an ideal sense. This is how total width could theoretically be compiled to native x64 machine code. Ideally, the total width function would be implemented in just a few machine instructions. The idea is that the compiler would know where the width property is located within the objects of the type we're dealing with here. Let's say that the width property appears in memory at 8 bytes from the start of each object. So all the compiled code needs to do is to retrieve a numeric value from offset 8 within each object, A and B, add the two numbers together, check for overflow, and return. So is this possible? Is it possible for a JavaScript compiler to just go ahead and compile the total width function in this way? And the answer is no. The main thing that gets in the way is that by looking at this function total width, the compiler cannot see or infer any type information. So is it possible for the compiler to know that this width property is going to be located at a particular offset, like 8, from the start of object A or B? No, because the compiler is stuck with not having any knowledge about the type of object A or object B, or what those memory layouts might be. So the compiled code will first have to go to some lengths to search for and obtain the width of property of A and of B. It's not at all as simple as looking up something at a well-known offset. After successfully obtaining the value of the width properties, another issue comes up, which is that there's no guarantee that the value of the width properties are in fact numbers. That's not something the compiler can just assume. And if they're not both numbers, then plenty more logic is going to be needed in order to implement JavaScript's extremely complex rules for applying the plus operator to operands of various types. All of this trouble fundamentally stems from the loosely typed nature of JavaScript, which leaves any compiler with very few hard facts to work with. So the final answer is no. Total width can't be compiled in such a simple way. Instead, it's going to take far more effort to implement total width, and that is very bad news. Because if we can't execute something as simple as total width in a small, efficient manner, then the engine is going to have a major problem getting decent performance when running any JavaScript programs of realistic complexity. So we are still left with this fundamental problem. How is it possible to execute JavaScript at high speed? An interpreter won't work because it's far too slow. But as we explored on the previous slide, a compiler is not going to solve our problems either, because the lack of type information will hamstring the compiler's ability to generate efficient code. There's also a second problem with using a compiler, which is that the compilation process itself takes a lot of CPU cycles, and that would make web pages load far too slowly. The solution used by all of the major engines is multi-stage execution. And here's how it works. When loading new JavaScript code to execute, the engine first starts by executing it within an interpreter. And this allows JavaScript execution to begin as promptly as possible, so web pages can load fast. The interpreter has a second job. While it's executing code, it collects runtime type information about the values found in variables. And this is known as profiling. Eventually, those areas of the JavaScript code that are running hot, such as loop bodies or functions that are called many times, Those are sent for just-in-time or JIT compilation. And by this time, enough type information has been collected so that the compiler can make some optimistic assumptions about the types that it will encounter. And on this basis, the JIT compiler can emit code that is really quite highly optimized. Incidentally, some engines expand this paradigm to include multiple stages of JIT compilation. The interpreter and the earlier JIT stages have faster startup times, but execute less efficiently. The later JIT stages take longer to start up, but final execution has better efficiency. Now, as we just said, the JIT compiler is able to emit efficient compiled code because it optimistically relies on certain assumptions about the types of variables, in accordance with the profiling data that was gathered. But these are only assumptions, not guarantees. Since JavaScript has no strict type guarantees, any assumptions about type could fail at any time. So the JIT compiled code still needs to contain type checks at strategic locations to make sure that its assumptions are still valid. And if it finds that some assumption no longer holds true, then the JIT compiled code needs to stop executing and immediately fall back to the interpreter in midstream. Chromium's V8 JavaScript engine calls this de-optimization, and we'll use that terminology. So this adds an enormous amount of complexity, both in the type checking logic and in the infrastructure needed to make it possible to switch from compiled code back into the interpreter in the middle of executing a function. But that's not all. Not only are JavaScript engines algorithmically complex, as we have just described, but the data structures that they use are complex as well. For example, when storing a JavaScript array, the data structure must be able to efficiently represent both sparse and dense arrays. A sparse array is an array that contains values at various indexes with gaps in between the indexes where values are defined, as opposed to a dense array, which is the more traditional sort of an array, where there is a single continuous range of indexes where values are defined. And if the array contains all integers or all floating point numerics, those are very important special cases that have to be optimized for. Furthermore, JavaScript allows arrays to define get and set methods on specific indexes, meaning that custom JavaScript methods will be invoked when those particular array indexes are accessed. And all JavaScript objects, including arrays, are allowed to have any combination of named and numeric indexed properties. Each of these combinations calls for certain optimizations in the way objects are laid out in memory. But what makes things really dangerous is that all of the above object characteristics can change at any time during execution, and this may require in-place modifications to the object's memory layout. Clearly, there's a lot of room for things to go wrong, very wrong. In fact, array operations are one of the very most perilous areas within JavaScript implementations. So here we're going to do a brief drill down into some of the specifics of how array elements are stored in memory. Please note that some of these details are specific to the way Microsoft's Chakra JavaScript engine operates, although the theory carries over in a pretty straightforward way to Google's V8 engine as well. If you create a JavaScript array containing only floating point values, that's an important special case. So the engine will represent it in memory as a native float array. This means that the JavaScript engine will allocate a continuous block of memory and pack it full of floating point array values, each stored in native form, by which we mean the natural and hence the most efficient form for the machine architecture that you're running on. Okay, so now let's say you take that array and now you place a new value into the array that's not a numeric. Let's say it's a JavaScript object. Now the array can't be stored as a native float array anymore. So the engine will do an in-place conversion of the array into a general array type. General arrays allow for storage of elements that can be of any JavaScript type, which includes objects. The storage for each element in memory must be able to represent either a numeric or a pointer to a JavaScript object in memory. Now the float elements can't be stored so simply as before, because the data in memory backing each element must also contain some additional information indicating whether the value is supposed to be understood as a numeric or as a pointer to an object. This should all become much clearer with an example. Suppose we create an array A, and into this array we put 2 floating point values and 2 JavaScript objects. Since this array does not contain exclusively numerics, the engine cannot store it simply as a block of floating point values in memory. Instead, each element in memory must be capable of representing either a numeric or a pointer to an object. And this is what we call a general array, as opposed to a native array. As you can see in the illustration, where there are indexes that point to a JavaScript object, as in the last 2 indexes there, then the storage for array A simply contains the pointers to those objects. But for the first 2 indexes, we need to store the floating point values 1.1 and 2.2 respectively. For these, the engine takes each floating point value to be stored and it encodes it in a special form that is clearly not valid to interpret as a pointer. And those are the invalid pointer values that you see in the first 2 elements. When reading values out of this array, the engine can reverse the process. After reading an item out of the array's memory, it will check whether the value is valid to interpret as a pointer. If so, it knows that the value is intended as a pointer to an object. If not, it knows that the value is an encoded numeric, and it will then reverse the encoding to reveal the original numeric value. We're going to need to refer to this detail later on, so please keep this point in mind. When reading data out of the memory of a general array, the engine tests the data to see whether or not it is a valid pointer. And it does this to figure out whether the data is supposed to be understood as a pointer to an object or as a numeric in encoded form. One final technical note on how JavaScript arrays are stored. A JavaScript array will not always be represented in memory using a single monolithic buffer. For the sake of efficient storage of highly sparse arrays, the engine also must support an alternative storage format. For this, V8 uses a hash table structure, but in Microsoft's Chakra JavaScript engine, an array can be split among several buffers, each representing a different range of indexes. Furthermore, the first buffer of the array might be stored inline, meaning that it appears in memory immediately following the array metadata together with it as a single allocation, again, for performance. And there are also metadata structures to help an array locate all of its buffers efficiently. The bottom line is, internal storage of JavaScript arrays is not a simple matter at all. And as I mentioned previously, all of these details of internal representations are subject to in-place conversion during script execution. These are some of the considerations that make JavaScript array handling prone to mishap. It can be summed up in the truism that complexity is the enemy of security. Everything we've discussed so far can be described as an incredible overhead of complexity, all introduced in order to fill the nearly impossibly tall order of boosting JavaScript performance to the levels demanded today. Finally, I'm going to round out my remarks on what makes JavaScript challenging to implement by pointing out that JavaScript has a ton of features that can interact in unexpected ways to create potentially hazardous conditions. I'm just going to quickly mention some of these property getSet methods, prototype chains, custom coercion functions, species constructors, proxy objects, dynamic scopes created with eval or through iframes, the ability for script to redefine built-in functions. The list goes on for a while, and there are a lot of opportunities here for abuse. After that introduction, we're going to start looking at some actual classes of vulnerabilities that come up and see exactly what it is that goes wrong. So to start with, it's a bit scary to say, but even the implementation of the built-in JavaScript library methods has seen significant numbers of bugs, and this is going to be the first category we'll examine. Where you really see this is in the array handling routines. Interestingly, array.splice has proven itself to be particularly difficult to get right. And we've already discussed quite a bit about what makes array representation tricky. So what goes wrong in the array methods? Often it's because an attacker can get script execution to happen in the middle of a library routine. And some ways of doing this include defining getSet methods that will execute when a particular index is accessed, or by defining a custom species constructor, or something else that will be called during the operation, like isConcat_spreadable. If an attacker can get script execution in the middle of a library routine, they might be able to use that to violate the assumptions of the routine in progress. And this might mean changing the array's size or type, or otherwise modifying some parts of the internal representation of the array that the library routine is assuming to be immutable during the operation. This bug here is a great example of a problem in array handling in the JavaScript, Chakra JavaScript runtime, and this one wound up being ultra critical. I love this one. If you take a look at the bottommost red rectangle there, ... is actually part of the source code. It's called the spread operator, and that turns array X into an argument list for function F. And when this line of code executes, the runtime will iterate over array X to read its elements and copy them into a stack-based buffer. But as you see at the top, the attacker has defined a get method for index 1. So when index 1 gets read, that script at the top runs, and when that runs, it changes the length of the array, making it either larger or smaller. By shrinking the array in mid-iteration, part of the stack-based buffer will get left uninitialized, which gives you an information leak. Or by enlarging the array, you can get a buffer overflow. In fact, it can overwrite a local pointer variable on the stack and yield a very nice write-what-where primitive. So with this one bug, you easily compromise the whole process. Where things get really interesting, though, is in the JIT compiler. Specifically, what's often found is that the JIT compiler emits code that fails to account for all possibilities. Recall that the JIT compiler writes high-performance code based on assumptions about the types of data that will be found in variables. The compiled code needs to perform type checks to validate those assumptions. Violation of an assumption may require fallback to the interpreter, known as de-optimization. If it performs too many type checks, then performance suffers, which defeats the purpose of the compilation. So the compiler contains a lot of logic around determining exactly when type checks are needed. And it's a tightrope. If the JIT compiler makes one subtle logic error and leaves out a necessary type check, it's typically catastrophic. And I'm oversimplifying a bit here when I speak about type checks. More generally, we should really speak of state checks, type being one specific example of state, and other forms of state include whether an array length has changed or if the array has changed in internal representation, such as from dense to sparse, or whether the in-memory representation of any object has been converted to a less optimized form. Array type checks are a frequent source of trouble. Whenever the engine manipulates memory that stores array elements, it first has to know the correct array type, meaning whether the array is a native array or a general array, and also whether it is stored in a form capable of representing gaps for missing elements, and so forth. Let's say we want to trick the JIT compiler into leaving out a check on the type of an array. How could we go about doing that? Well, we're going to have to figure out how to write some gimmick that the compiler will think is harmless, while it really changes the type of the array. Because the compiler thinks that the gimmick cannot change the type of the array, it won't insert a second type check before that second array access shown. For the sake of performance, it will rely on the type check that it performed at the first array access. Let's see what could happen in this case. As you can see here, originally array A is a native array because it contains exclusively numerics. So its contents are written in memory as just a sequence of floating point values written in the standard native format. Suppose that our gimmick overwrites the last array index with an object. Then the engine is going to convert the entire array in place into a general array form. Recall that in a general array, if there are some numeric values, they are stored in a special encoded form that distinguishes them from pointers. And what you see there on the right-hand side of this slide is what the array looks like in memory after the in-place conversion takes place. Now, consider what happens if the JIT compiler fails to realize that our gimmick may have changed the array from a native array to a general array. When the last line of JavaScript code shown here executes, the JIT optimized code thinks that the array is still in native form. So it thinks that in order to store the value 4.4, it simply needs to write a native 4.4 into the array's memory, like so. But this is very wrong, because a native unencoded floating point value should never get written into a general array. In fact, this is already a critical vulnerability. Why? Because later on, when this array element is read at some point in the future, at that point, the JavaScript engine will be in a state where it correctly identifies the array as a general type array. So when it reads that native 4.4, it will apply the invalid pointer test to determine whether it should be interpreting this value as a pointer or as a specially encoded numeric. And here the attacker has the upper hand, because the attacker can easily choose this native floating point value so that it will be treated as a valid pointer. And this allows the attacker to forge a pointer of any desired value. But it actually gets even worse. Consider this code here. All we've done is to replace the final line of code with an array read instead of an array write. And in this case, we're reading from the last index here. What's going to happen? Since the JIT compiler has failed to recognize that our gimmick may have changed the type of the array, it continues with its assumption that the array is still in native representation. So it implements this final array access as a simple read of a native float from memory. But what's in memory there now? It's not a float, it's a pointer to a JavaScript object. And whatever the numerical value of that pointer is, it's going to get revealed to the attacker's JavaScript code in the form of a floating point number. And granted, this number is going to look rather garbled to the naked eye, but it only takes a few short lines of JavaScript to decode it and recover the exact 64-bit pointer value bit for bit. So we see that with one cunning gimmick, an attacker can both reveal arbitrary object pointers as well as forge arbitrary pointers to be injected into the JavaScript execution. And these two capabilities are sufficient to compromise the security of the entire process. So, what can we use for the gimmick? There have been lots of things that have worked. Here is one example. It's simplified slightly for clarity. The attacker defines an object, evilObj, which is a JavaScript proxy object having an enumerate trap. And that means that anytime that you enumerate over the properties of this object, evilObj, a custom script is going to run. And this custom script changes array A from a native float array to a general array by inserting a non-float value, namely an object. Then the gimmick is to run a for-in loop over evilObj. And as we have discussed, the JIT compiler fails to recognize that executing this gimmick, in this case, the empty for-in loop, can have an effect on array A. So it does not protect the final array access with a type check. Sometimes the gimmick can modify the array without actually having to achieve arbitrary script execution, like in the previous case where we had a custom method that would execute in the middle. Have a look at this gimmick, which was discovered by Loki Hart of Google Project Zero. Here the gimmick is to assign an object into an index of this. Now, there's a JavaScript feature called function.call that allows you to specify anything you want as the this parameter when calling a function. And the JIT compiler fails to take into account the possibility that this could be an alias to A. So when the code assigns into this sub2, it's actually causing an unexpected change to array A. This is a good example of one of JavaScript's many idiosyncratic features that can produce strange interactions that the JIT compiler then has to deal with properly. Here's an incomplete list of gimmicks that have worked. The first group shows coercion issues. In each example, in the first group, evil is an object that will be coerced to either a numeric or a string, which will then invoke the attacker-specified coercion script function, and that the JIT compiler was not foreseeing that to occur. And the second group shows various other techniques not related to coercion. As a part of new evil class, parentheses A, it's creating a new object of type evil class. And the trick is that if evil class is simultaneously a proxy, then it is possible to run script within the proxy's handler method. And this is a great example of how weird JavaScript can get, where you can have a class that's simultaneously a proxy. V equal evil.x, the JIT compiler was thinking that this was a simple property access, whereas in fact it was calling in a custom get prototype of method in one very special case where evil is an object that originates from a separate script context like an iframe. And finally, that bottom one there, math.max.apply, was found to cause unexpected script execution if the attacker name squats on the built-in math.max function. And in each case on this entire slide, when script execution happens, the attacker can use that as an opportunity to make an unexpected modification to array state. And sometimes you can find a gimmick that has the desired effect of modifying an array without going through the route of arbitrary script execution. We already saw one of these examples before. That's the top one. Here's a couple more examples. Very interesting. Setting any object's proto-property to an array instance will automatically convert that array to a general array in Chakra, but the JIT compiler was not accounting for that possibility. Finally, if you prepared a special array, evil R, that had a target array in its prototype chain, then calling evil R.reverse was affecting the target array. And again, the Chakra JIT compiler did not account for that possibility. There's a lot more examples. These is just to provide a window on how difficult it is for the JIT compiler to implement correct logic. In this final section, we're going to examine one more class of JIT compiler vulnerabilities having to do with errors in a component known as the typer. The typer is one major component of Chromium's V8 JavaScript engine. It's responsible for deducing known facts about the types found within variables. And it also deals with partially known information. For example, if it can be deduced that a variable must contain one of several known types, such as if it may be known that it definitely contains an array, but it is not known which type of array in particular. When it comes to integers, the typer takes on an additional responsibility. It also tracks what may be known about the range in which the integer can fall. For example, it may be known that the integer must be within the range from 1 to 100. As the data then flows through arithmetic operations, the typer does what it can to propagate deductions about the possible range of resulting values. The code shown here provides an example of why it is useful for the typer to be able to track the range of integers. This is a loop that iterates over an array, and in a naive implementation, before each array access, it would have to perform a bounds check. But the typer can help a great deal in this case because it can propagate deductions about the variable I, and it can establish that I will always be an integer and that it will always be within the proper range. And capitalizing on this, the JIT compiler can remove all bounds checks shown here, significantly enhancing performance of the loop. From a security perspective, though, this places a heavy responsibility on the typer to get all of its deductions exactly right, because any error could result in the erroneous removal of a bounds check in a case where the check really needs to be performed. Let's take an example of how faulty output from a typer could impact security. In the red rectangle that you see here, the JavaScript code is making a strict comparison between an integer and a string. The typer can deduce that these two values will never be strictly equal, so that the variable b has the known type of Boolean false. In the next line, variable b is being used in an arithmetic multiplication. And according to the rules of the JavaScript language, a Boolean value used in this way will be coerced into either a 0 or a 1. 0 for false, 1 for true. As a result, variable c will receive either 0 or 1337, depending on the value of b. This is a technique that can be used to amplify any error in b. But in our case here, the typer correctly determines that b will always be false, so it deduces that c will always be 0, And on this basis, the JIT compiler will omit the bounds check before the array access on the last line. In this case, all goes well. To produce a failure scenario, we'll need to replace what's in the red rectangle with some other expression, one where the typer draws an incorrect conclusion about whether it will evaluate to true or false. An example of this came in November 2018 with the EXP-M1 bug found by Tsuro of Google Project Zero. He found a circumstance where the typer would incorrectly identify the output of a certain obscure built-in function called math.expm1. And this is the tricky part of the specification of this function, is that it's possible to get out a value of -0. And this happens when you pass in a value of -0. And this is the essence of the bug. The math.expm1 of -0 will produce -0, but the typer wrongly assumes that a return value of -0 is not a possibility. So when the typer tries to determine the result of the above expression, it will wrongly conclude that the answer is false when in fact it's going to be true. And plugging this back into the bounds checking scenario that we explored a couple of slides back, this is basically what you would want to do in order to exploit the EXP-M1 bug. The idea is that the typer would wrongly conclude that B is false, and that consequently C is 0, so no bounds check is needed on the last line. While in reality, B will be true, and C will be a large number. And then according to the large number according to the amplification factor, and then the attacker can read or write outside the bounds of this array. I see I have a red light. I was going to go into a bit more about the exploitation of this. Just another couple of minutes. Is it good? Okay, great. In practice, if you were to try this, it will not work. By which I mean that even at the time the bug was originally found, and the typer was still exhibiting the incorrect behavior and was not yet patched, this method of exploitation still did not quite work. And for this reason, Google originally believed that this bug was not exploitable, and they assigned it a lower priority. And the essential difficulty in exploiting this was that the incorrect typer result, which indicated that EXP-M1 could never return -0, was also being used elsewhere in the JIT compiler to inform how values needed to be converted when passing parameters into object.is. And what was happening because of that is that the -0 value was being silently replaced with +0 before object.is ever got to see it. Eventually, Google researchers did discover a route to making this bug exploitable, and then this was made as an exploitation challenge as part of the 35C3 CTF in December 2018, leading to multiple outside researchers finding their own solutions. Among those was Andrea Biondo, who is also a member of the winning team, and the essence of his solution is shown here. Most critically, what he did was that -0 value to pass into EXP-M1 is provided through a parameter x, and during a preparatory call, x is set to a numeric value in string form. Since now the profiling information indicates that x is not always a numeric, the JIT compiler is forced to treat EXP-M1 as a full-fledged call into the JavaScript runtime library, and a side effect of that is that when EXP-M1 is executed in that way, no further internal conversions are needed between the output of EXP-M1 and the input of object.is. So the -0 flows right in. Also, in the second parameter to object.is, it's provided via a field on a locally defined object. And this helps to ensure that the compiler does not realize too early that the second parameter is the fixed value -0. Otherwise, the compiler would omit this entire operation, again, based on the typer's incorrect assurance that exp_m1 never returns a -0. And then after these tweaks, the JIT compiler will omit the necessary bounds check, and so far from being non-exploitable, this exp_m1 bug is highly critical, allowing out-of-bounds array reads and writes, and that is how the obscure exp_m1 math function and the value -0 became legend in JavaScript engine security research. We're a little late on time, so I'm just going to skip the summary. Thank you so much.